Continuity, Part 5. So this is just more of showing that a solution exists, even if we can't find the exact solution, by using the intermediate value theorem. And in order to use the intermediate value theorem, we have to show that a function is continuous on a closed interval from a to b, that n is any number between f of a and f of b, and that f of a does not equal f of b. If we can do that, then we can show that there exists a number c in that interval a to b such that f of c is equal to n. Use the intermediate value theorem to show that there is a root of sine of x plus x is equal to 3. In order to make our lives easier when we're using the intermediate value theorem, what we like to do is solve for 0. So this is the same equation as sine of x plus x minus 3 is equal to 0. These will have the same solution or root. Then we want to state the intermediate value theorem. So suppose f is continuous on the closed interval a to b, and let n be any number between f of a and f of b, where f of a does not equal f of b, then there exists a number c in AB, this time the open interval, such that f of c is equal to n. So now we want to state and justify continuity. So here our function will be this, and I'll just use a different color. And our n, the output that we're interested in, will be 0. So we need to say that f of x is equal to sine of x plus x minus 3 is continuous on the interval, we'll say from negative infinity to infinity, because this is continuous for all real numbers, and we're just not quite sure what our interval a to b is yet. So we know it's all real numbers, so that'll definitely include whatever smaller subinterval we come up with. And it's continuous over this interval because each of the functions that make up this function, so sine of x, x, and negative 3, are continuous functions themselves. Because we have sine of x is a function we know is continuous, x is a constant function, a linear function we know is continuous, and negative 3 is a constant function that is also always continuous. Now, there are two main ways to find f of a and f of b for this problem. One is like the easier way, but you're going to have a wider margin of error, and 1 is the more difficult way, but it's going to give you a smaller error band, so it's a little bit more accurate or precise. We'll start with the easier but more error-filled way. So let's find f of a and f of b. And I'm finding them. Forgot to write find. Okay, so n is equal to 0. And since we don't have an interval, that means that we need to find f of a and f of b, where 1 is positive and 1 is positive. I mean negative. So where 1 is positive and 1 is negative. So let's just start by substituting something that's nice and easy to evaluate. So at f of 0, we have sine of 0 plus 0 minus 3. So that'll be 0 plus 0 minus 3, which is equal to negative 3. So that means that we have one of our values. So we have f of 0 is equal to negative 3. That means that now we need to find a positive number. Now, we don't know too much about sine of x plus x minus 3. But what's kind of nice is we do know that sine of x is a bounded function. So much like we've done in the past for like a squeeze theorem, we can say that negative 1 is less than or equal to sine of x, which is less than or equal to positive 1. And then we can transform this middle chunk to look like that sine of x plus x minus 3. So we'll add x minus 3 to each part of this. So we have negative 1 plus x minus 3 is less than or equal to sine of x plus x minus 3, which is less than or equal to 1 plus x minus 3. So we have x minus 4 is less than or equal to sine of x plus x minus 3, which is less than or equal to x minus 2. And we're looking for this function to be greater than 0. And we're trying to find an input that makes that true. So we want to substitute something into this function that will make it so this x minus 4 is a number that is larger than 0. Because we're looking for a positive number specifically. We already have a negative, now we need a positive. So I'm going to substitute in x is equal to 5. So then we have 5 minus 4 is less than or equal to sine of 5 plus 5 minus 3 is less than or equal to 5 minus 2. So we have 1 is less than or equal to sine of 5 plus 2 is less than or equal to 3. And what this means is that f of 5, which is equal to sine of 5 plus 2, is going to be a positive number. Because if it's greater than 1, it's going to be greater than 0. So we have our f of a and our f of b that we need. Now that we've found an a and a b and an f of a and f of b, we need to state our conclusion. So we'll just summarize our hypotheses that we've shown are true so far. So since f of x is continuous, on the closed interval from 0 to 5, so a to b, and f of 0 does not equal f of 5, and zero is between, is not pretty handwriting, f of 0 and f of 5, we can conclude that there must exist a number c in the open interval from 0 to 5 such that f of c is equal to 0. Thus, sine of x plus x minus 3 equals 0, and sine of x plus x equals 3 have roots on 0 to 5 by the intermediate value theorem. But now let's look at the more difficult but less error-filled way, so a band that's even closer to that solution than 0 to 5. So let's go back to the point in the problem where we were finding f of a and f of b. We had already found that f of 0 is equal to negative 3. So we'd already found a negative output. Since n is equal to 0, that means that now we need to find a positive output. So let's take a look at this function. Sine of x plus x minus 3 is going to be greater than 0, so positive, when, well, let's just add 3 to both sides to this. So when sine of x plus x is greater than 3. So we're trying to add sine of x and x together and get a number that's greater than 3. And a good place to start is just by trying to find where sine of x and x are both positive. Because if they're both positive, we're at least heading in the right direction and there's like a smaller range of values to guess. Well, x is positive when x is positive, so that's not too bad. But let's look at the sine of x. So if we graph sine of x from pi to 2 pi, this doesn't look perfect, but it doesn't have to be too perfect. We can see that on the interval from pi to 2 pi, sine of x, remember this is just the graph of sine of x, not our whole function, sine of x is positive from 0 to pi. And pi is about 3.14. So that means that if I'm between 0 and pi, and I look at 3, which is between 0 and pi, well, sine of 3 is going to be positive. I'm not exactly sure what sine of 3 is going to be, but it's positive. And that means that if I look at f of 3 is equal to sine of 3 plus 3, so I'm just substituting x in there, sorry, 3 in for x, minus 3, so I'm going back to my original function here. Well, 3 minus 3 is 0, so f of 3 is equal to sine of 3, which is a positive number. And I could have used numbers other than 3, but this works out nicely because of this 3 minus 3. So I intentionally chose 3 because of this minus 3 here. So that means that I have my A and my B that I need. So I'm looking at the interval from 0 to 3. And I have a positive and a negative output on that interval. Now all that's left is to state our conclusion. And we'll start by summarizing the hypotheses that we've met so far. So, since first thing is that f of x is continuous, on our closed interval from 0 to 3, because those are our inputs, and f of 0 does not equal f of 3, and 0 is between f of 0 and f of 3, there must exist a number c in the interval from 0 to 3 such that f of c is equal to 0. Thus, sine of x plus x minus 3 equals 0, and the equation we were actually interested in, sine of x plus x equals 3, which is the same equation, it has the same solution set, have roots on the interval 0 to 3 by the intermediate value theorem. So this problem had two main ways to find f of a and f of b. One was a little bit easier, one was probably a little more difficult, although I guess that is an opinion, so you might have found the reverse difficulty is true. If you're in my class, you can use whichever method you want, but just know that in the real world, what we'd probably want is to minimize that error. And there's ways to even get a smaller error band, but these suffice.